To understand the end, you must start with the beginning. The Donald Judd Donut is no exception to this rule. Its form finds its genesis in a work made by Donald C. Judd in 1964. The Donald Judd work appears as a long square tubing which rests on its edge. The tubing forms a rectangular donut shaped by making 4 turns to loop back onto itself like a serpent without a head or tail. Unlike the serpent, however, this work sits outside of nature, forged using the power of mathematics and technology. The essence which is created in Donald Judd's work due to these elements lay at the central core of the Donald Judd Donut also. Today I will present the mathematics which pour the foundations of the work and the problems which had to be overcome in order for it to reach its donut shape. From a bird's eye view, we look upon 2 simple shapes, a square and a rectangle. I'm showing you both in order to explain what happens when you want to curve each one around a corner. Working with the square, we can see that the curve which the object takes to make it around the corner is in the shape of a circle. This is due to the perfect nature of the square, having all sides equal to each other. This means that the radius of the curve in a square is consistent. The rectangle, on the other hand, has curves in the shape of an ellipse due to one of its sides being greater than the other. This means you get 2 radiuses. These images seem simple enough to understand visually. However, once we introduce mathematics, we find one shape takes on a more complex attitude than the other. This is all revealed once we try to find the circumference of the curves found in the object. The equation on the left shows the equation of the circumference of a circle. The equation on your right shows you the equation for the circumference of an ellipse. You can see straight away which one carries that complex attitude I was speaking of earlier. I'm getting too much complex attitude right now, so I will pause on the explanation of this portion of the shape to revisit later on. Taking a break, we will visit the simpler section of the shape, which are its straight sections. This portion of the shape is one which is much easier to understand, with equations carrying much less of complexity. Firstly, if we approach the shape from its front elevation, we see the shape of a square, tilted to make a diamond. We know that all sides are equal in this shape, which tells us that the negative space around the diamond is made up of right-angled triangles. This intelligence will allow us to calculate the length of each side of the diamond. Now, from above, we are told that Judd's work from the outer edge of one of its rings to the inside is 39.5 centimeters. The Donald Judd Donut is 1/10 of the size of the Judd work. Using this knowledge, we now know that the thickness of the Judd Donut is 3.95 centimeters. Now, the power of mathematics will help us to find the length of each side of the diamond. Using trigonometry, we know that a squared plus b squared equals c squared. And we also know that the sides of A and B are the same as it's a perfect diamond. Revisiting the triangles which form in the negative space of the shape, we find that A and B are the same and equal to half of 3.95 centimeters to make 1.975 centimeters. We plug this number into the equation a squared plus b squared equals c squared to find that c squared is equal to 7.80125. We take the square root of this number to find the length of c, which is 2.793 centimeters, or 27.93 millimeters. This number is rounded to the nearest 3 decimal places. From now on, we will work with millimeters rather than centimeters as a standard unit of measurement. This is due to millimeters being much more accurate. We will also round our measurements to the nearest 2 decimal places, as our technology which we will use to measure limits our accuracy. These measurements allow us to create a net which will make the diamond shape by folding a net every 27.93 millimeters until 4 folds are made to complete the shape. This length of 27.93 millimeters for each side of the diamond remains consistent throughout the donut, including the curves. Now that we know the length of each side of the diamonds which make up the shape, we must find out how far into space each straight extends. Looking at Judd's work, we can assume that each side is split into thirds. The first and the last third start where the curve meets one straight and finish where it meets the second straight. We know each length from Judd's work is 236 centimeters and 198 centimeters. Dividing these numbers into thirds and converting them to millimeters, we get 78.66 millimeters and 66 millimeters. We have now calculated the complete shapes for each straight in the Donald Judd donut. There are 4 straights in total, consisting of 2 different nets. Each net can be cut from a single sheet of cardboard and joined at one point. Now that we have established dimensions of the straights, we move forward onto the complex attitudes found in the shape's curves. We know from earlier that the curves found in the Donald Judd donut are in the shape of an ellipse, not a circle. There are 3 ellipses in the curves on the shape: an ellipse for the inside, middle, and outside curve. We need to calculate each ellipse's circumference and then divide them by 4. We divide by 4 as the ellipses in the curve consist of only a quarter of a whole ellipse.
Let's get on.
I'm getting there. I will show the mathematics behind the first curve, as we can repeat this to find the circumference of the other curves. We calculate the circumference of the ellipse by finding its vertices. These are the points of the ellipse where, if you were to plot the shape onto a graph, the vertices would be where the ellipse crosses the x and y axes. The vertices here are labelled A and B. These will be the numbers which we introduce to an equation in order to find the circumference of the ellipse. We do not require a perfect calculation for the circumference. In fact, we prefer a bit of inaccuracy to create a little wiggle room. The vertices here are labelled A and B. These will be the numbers in which we introduce to an equation in order to find the circumference of the ellipse. We do not require a perfect calculation of the circumference. In fact, we prefer a little bit of inaccuracy in order to create a little bit of wiggle room when joining the shape together. This is because the curved sections of the shape will be slightly overlapped by the straight sections, just as in the case of the Donald Judd work. Since we are only requiring a rough, rounded calculation to account for overlap, we use a simplified equation to calculate the circumference of an ellipse. The circumference is approximately equal to pi times the sum of A plus B. We also need to divide this answer by 4 in order to get a quarter of the ellipse. The outcome of this will give us about 55 millimeters, rounding up to 2 significant figures. Using this equation for all 3 ellipses, we get the following measurements: 55 millimeters for the inside, 82.5 for the center, and 113.6 millimeters for the outside ellipse. These measurements will be crucial in the construction of the curved net. With the technology available at the time of the construction of the Donald Judd donut, we would be unable to create a perfect curve. The material used in the construction is cardboard, a material which requires sections to be cut out of it in order to curve around a corner in the way we are needing it to. The Donald Judd donut's curve is split into 7 different sections. 7 is chosen for its significance in culture and mathematics. In mathematics, 7 is a prime number. In culture, 7 were how many days it took God to create Earth. This is also the same number of days it took to create the Donald Judd donut. We mustn't rush to split our circumferences up into 7s, however, as if we were to do this in even sections, we would get a quarter of a circle and not an ellipse. Therefore, we need to find a ratio in which will increase the length of each section as the curve goes along.
Oh my gosh, that was so hard.
This looks like it's going to be harder. To find the ratio, we will use a gradient. This is found through the right angled triangle which is formed against the vertices of the ellipse. Here, however, instead of finding the curve, we only require a straight line. This means that our equation is much more simple. The equation we use for this is simply the rise, 39.2 millimeters, over the run, 26.5 millimeters. With this, we get a gradient of 1.48 rounded to 2 decimal places. We know that each curve in the shape runs parallel to each other, so we do not need to change the gradient to calculate the different sections on each curve. Now that we know the gradient, we must find what each of our lengths are. We know 3 things about the equation for certain. A. There must be 7 sections. B. They must all be multiplied by the gradient. And C. All the sections added together must equal the circumferences calculated earlier from the ellipses. The only thing which we don't know is the constant, which does not change per section. This will be x. Knowing what we do know, we can create an equation to derive x. The equation we gather is c equals x multiplied by 1.48, which is the gradient, multiplied by 1, which is the section number, plus x multiplied by 1.48, which is the gradient, multiplied by 2, which is the second section number, plus x times 1.48 gradient times 3 section number, and so on until all 7 sections are multiplied and added together. Now we have this equation, we can find x for each curve by plugging in the circumference accordingly. With this we get x equals 1.32 for the inside, x equals 1.99 for the middle, and x equals 2.74 for the outside. Plugging back into the equation, we can pull out the length of each section by multiplying the constant by the section number by the gradient. For example, if you wanted to find the length of the 5th section for the middle curve, you would go 1.99, which is the constant for the middle curve, times 5, which is the section number, times 1.48, which is the gradient. This would tell us that the 5th section on the middle curve would be 14.73 millimeters in length. Now that we have the calculations of each section, we can start making the nets. In total, there will be 16 nets, 8 for the inside and 8 for the outside of the curves. The measurements for the middle curve will be used in the creation of both the outside and inside net, as the middle curve is where they shall meet in harmony. Each section of the nets will take the shape of an isosceles trapezium, with the length from the angled sides being equal to that of the length of the diamond sides, which we calculated before. This is so that when each end of the curve meet back with the straight sections, they will be the same size. Ruling up each section using this information from earlier, we are able to create the nets for the curves, repeating the process until all 16 nets are made. From here, we simply attach each net together and forward the sections to create one whole curve. Now that we have created the curved section, we are able to attach it to the straight section, and in repeating this process find ourselves with the cardboard shell of the Donald Duck donut. Extra strengthening of the shape is added for stability with an internal framework. An orange paint is kissed upon the cardboard, allowing it to shine in its final form, the Donald Duck donut.